Okay, can you see this one?
Yep, perfect. This is
okay. Sorry.
super. This is great. Okay, just let me know when you're ready.
I think I'm ready now. Yeah.
Okay, fantastic. Okay, excellent. So our next speaker is Mandy Chuang from Harvard University, who will tell us about mirror symmetry for rank 2 cluster varieties. Mandy, in case there are questions in the room, it would be fantastic if you could repeat them before you answer them so that online we can also hear what the question is that you're answering.
Sure.
Okay, super, thank you. So it's all yours.
Okay, thank you very much for coming here. Thank you very much for all the online participants, especially thank you for all the technical difficulty we are encountering. Today I'm going to talk about mirror symmetry for rank 2 cluster variety. Okay, again, this is a very exciting, interesting talk too. As the second speaker after Mark, I guess my responsibility is to make things more understandable. So here we go. I'll basically repeat what Mark said for his first line. We have cluster algebra, as most people here know, were introduced by von Mises-Minsky, defined by iterative step using SID and mutation. And then Mark was telling us this schooling procedure, but in terms of cluster variety, what we can do is we just turn the SID, which is a set of n variable Laurent polynomial in n variable, into algebraic torus. And then to us now, the mutation procedure will be birational map between two tori. And then now this is how we are saying, which is what Mark is saying, we glue the torus by this mutation map. So this is how we can see cluster variety, and our favorite A2 example, which is how we define glue this two torus by this mutation map. And then as Mark said, this is this Gross-Hacking-Keel conservation paper that develop theta basis for cluster algebra using scattering diagram, Booklet 9, and all these things. So we repeat in case we forget things after 10 minutes. We start with a rank and lattice for scattering diagram. We are going to nail down to rank 2 very quickly at some point. And then dual lattice, a scattering diagram is a collection point with some finiteness condition. That is what Mark said. When we have it only up to finite order, we only have finitely many walls. And what are the walls? The walls are consist of two data. The first one is some cone lies in some hyperplane, and then we have a function associated to wall, which we are calling for wall function, and which is a polynomial or power series here in this variable that is coming from the direction of the wall. And then can I do it? Okay, this is our favorite example, the A2 example. Let's look at here, which is this is our scattering diagram. We have 3 walls, and then to each wall we associate to we have wall function that associate to each wall. You can see here I have the point -1, 0, and then this is my polynomial, and this is a scattering diagram for cluster algebra of type 2. And again, as Mark said, we have something called path order product or wall crossing, which is we cross a wall, and this is the gamma that we cross a wall. And crossing a wall gives us an automorphism, which again, if we have time, we can go into the deep, go to the definition in detail, but let us illustrate everything today by an example. So this wall crossing, the automorphism we are having, say we apply on this monomial set to the -1, 0. Here we are the A variable, so the variable are A1, A2. What we do is we keep the monomial and then we multiply this wall function. And then here we have some exponent, but in this example, it's just 1. And if we expel everything out, it's just 1 plus A1 over A2, which is exactly the same mutation that we saw before. So here you can see within the cluster complex, the wall crossing are just basically the cluster mutation that we are very used to. So another thing we need to be careful is consistent scattering diagram. Sort of Mark talk a bit about it. So roughly speaking is we have this wall crossing or path order product. And yes.
Why is A1 plus A1 over A2?
I think you're correct. And that might be just a typo. Thank you very much. Okay, great. Yes. Thank you. And then here is a consistent scattering diagram. Is if we consider a path that looping around the scattering diagram, this path order product will be composing it will be identity. So that is it. That is scattering diagram that we have a few minutes before, and then we have theta function. The motivating example that we'll have is this torus, two-dimensional torus, that we have the function on the torus are just Lorentz polynomial that is linear combination of monomial indexed by lattice in rank C2. So this is the idea. So what we do is like this theta function is we wanna like do an analogous or the original JHKK setup, which is what we have is we have this lattice and then we define function from on those lattice. Again, there's a really long definition and we illustrate everything by an example, which is to each point. We are going to talk about this answer late in the later part of our talk, but let's just say this is a lattice, and then we associate this theta function on it, which is coming from a collection of broken lines with initial slope coming from this M and endpoint Q. So this is our endpoint here. We have this is an example we have, which is -1, 0. This is one broken line that it doesn't bend, and this is the other broken line that bend over the wall. And then this theta function is we sum up all the monomial associating to the final piece of linearity, and this is our theta function. And what is more, and it doesn't appear, okay, it is. Again, here, this motivating example is all the function on the tori can coming from linear combination of this monomial, and the multiplying different monomial also give us like another monomial, which is or the vector space spanned by those monomial will give us all the functions. So this is the same thing we look for the multiplication between two theta functions, which can be still expressed as linear combination of other theta function. And so we can see here the collection of theta function carry the it's just an algebra or carry algebraic structure, so that we have custom algebra, or later on we can look at the algebra and take the spec of it. So this is a very rough and quick recall of what we have in scattering diagram and theta function. So the next thing, which is going back to what Mark said in his talk. In his talk, he talked about Lagrangian fibration, all the Lagrangian torides and all this way. So how we can see it in scattering diagram, which as Mark said, like scattering diagram in certain sense a tropical picture of the Lagrangian fibration. And the wall in Mark's talk are just Maslov index holomorphic disk, and again we cannot see anything. Holomorphic disk. Here the tropical version, we are going to see tropical curves or tropical disk, which is in Hima's talk yesterday. We have tropical curve. Other than we go straight line, the first example we have is this trivariant graph, which Anima said it yesterday, is a weighted graph with some balancing condition. The balancing condition is at each vertex. We look here, unlike Anima, we look at primitive vector, but tropical curve will carry weight. That is how we cheat with the non-primitive cases in our setup. So, but here we look at the primitive vector associated to it, as hint there might be some weighting. But let us say here the balancing condition will be summing out all the outgoing direction will be 0. That is our tropical curve. And then we have another more example, which is something like that. And we got a bunch of examples yesterday already. So now the question next is how we can see those tropical picture, tropical curve, tropical disk in scattering diagram. So let us go now. This is our only example. This is our scattering diagram. Can you see a tropical curve here? Okay. Here, yeah. Can you see a tropical curve here? I don't know. You're laughing because you know the answer, or pretending that this is, like in writing lecture. Okay, this is a tropical curve, and you can see here at this vertex, when we sum the outgoing direction, it is 0. So this is actually what Max said in his talk, the Gross-Hacking-Keel paper, which is we are going to talk a few things about that paper. But the first thing is actually this wall function, instead of now we see it as custom mutation map, the coefficient, when we take log or just the wall function itself, the coefficient here are actually corresponding to tropical curve counting. So you can see now how this getting diagram picture incorporate what Lin rules idea philosophy about building mirror Maslov index holomorphic disk. So this is how we can elaborate the picture from Biconkim's and Yu-shen LIn's work. The tropical curve counting equals to holomorphic curve counting. And what I do, oh, by the way, this talk is based on a joint paper with Sam Bardwell, Hansol Hong, and Yu-shen LIn, and we just posted like 2 weeks ago, which at the point I just arrived at the institute, so it's still fresh. So what we do is we turn things in the 4 theory sense. So this tropical discounting, we use the tropical holomorphic correspondence to construct Lagrangian fibration, and then we can see them as Maslov index 0 discounting. Is here we have having Maslov index 0 because it is like in Max talk we take out the boundary, so the intersection is 0 here. So this is what we have, and here is a super rough story that we can have in mind. So what we have now is this is a rank 2 setting. So we look at a collection of primitive vectors in C2. And then here we start with a toric variety, which we define a fan that coming from those primitive vectors. And then the next thing what we want to do is you can see it's like entirely, the idea is like from Mark's talk. And then the next thing is we look at the divisor. And the divisor we are looking at is a divisor associating to this one-dimensional way of the fan. And then the next thing what we do is we want to bow up at the point on those divisors. We'll be more precise when we go to the cluster case. So, but then here is it, we have this bow up of toric variety, and then we gross point-dependent but want to give some illuminative in calculation of those space. So what we can do is we have those fan here. This is our fan picture. The scattering diagram we are thinking is associated to each point here, each point of bowing up. We associate a wall, which is coming from this whole line, coming of this mi, and then we associate a function 1 plus z to the mi. But this is just to each point of bow up we associate to the wall. So the whole scattering diagram we are thinking, the initial scattering diagram we are thinking is we look at the collection of all those walls that we have, and then the resulting scattering, we'll look at the consistent scattering diagram that containing this initial one we have. And the consistent scattering diagram will give us the next slide. The Gross-Hacking-Keel paper will tell us that for the consistent scattering diagram containing this initial one, the coefficient will give us some counting of the genius 0 curve. It is like in Max talk when he's answering grad, which is how touching the divisor and some tangency condition that this is talking about. And the one thing we'll use actually in our paper is consistent scattering diagram are unit up to equivalence. So once we know the initial scattering diagram is the same, we know the final consistent scattering diagram are the same. So that's it. That is the illuminative geometry. So the next thing what we should be doing are we go back to the cluster algebra setting, and with unknown reason, it is not showing again. Okay, it is still okay. So this is what we do. Gross-Hacking-Keel give the algebraic geometric interpretation of scattering diagram. What we have with Bardwell-Evans, Hansol Hong, Yu-shen LIn is we literally construct the Lagrangian fibration, and then we construct the holomorphic disk, and then we construct the scattering diagram from the Fourier point of view, and we use the tropical holomorphic correspondence show that the two scattering diagrams are the same. So there we can see like this GPS scattering diagram, the counting does carry the family 4 meaning, theory meaning. So as a cluster person, I guess it is like, how do we care? Why do we care all this thing? What does that mean in terms of the cluster variety sense? So let's just go into more precise definition of cluster variety, which do we have enough time?
Yeah, you have until 2:25.
Oh, sorry. Oh, you want to close this? Okay. I'm sorry. I'm sorry for too many. Maybe my talk is just too technical. That's why we have too many technical issues. You're going to see it's like it's going to be quite technical. But anyway, we have said it's defined by something we call seed data and fixed data. And what are they? Which is we have a skew symmetric, we have a lattice, we have a skew symmetric form, we have the integer di. The di are just making the skew symmetric form into skew symmetrizable. And the seed now, instead of the variable, we are having a basis of the rank. And then we look at the dual basis and everything. And then the Green torus procedure is we associate to the lattice with a torus, which is we have the lattice, dual lattice, and then we have the dual tori. And then we glue the torus. This is the A case, as the notation suggests. This is the X case. And then we have the two type of mutation, the A mutation and X mutation, which is given by this. The reason I type it up is so technical is, okay, let's, like here is the X mutation is 1 plus the CEI, which is the mutation by here, and then A mutation is 1 plus set to the VK, where VK is coming from adding the EK by this skew form. We are going to go back to this first later, but this is the A and X mutation. The one thing I want to talk about in this talk is we have this mirror symmetry between the A variety and the Lennon's-dual of the X variety. So what is the Lennon's-dual? Actually, what Lennon's-dual is just we look at the original exchange matrix, we look at the negative transpose of it, and that's it. And then, but we want to turn it into this seed data and fixed data language. So this is what we are going to do. The Lennon's-dual lattice is we look at the dual lattice, which is coming from answer that is spanned by DIEI. And then we look at other integer that this one is actually giving us the transpose of the original exchange matrix. But anyway, let's just look at an example to understand how that goes. Two-dimensional example, scale form is 0, 1, minus 1, 0. The two integers are KL, and they are co-prime to each other. So you can imagine this is K and this is L. And then the A mutation will be 1 plus A1 to the minus K and 1 plus A2 to the L. And then on this side, we want to look at the Lennon's-dual X mutation. So if we do the calculation, we'll get the two mutation of this one. Here, the illustration is you can see, very roughly speaking, we pull out the exponent from the A to X, and we flip the exponent between this Lennon's-dual. This is not that pity as long as we have 3 integers, but I would say this is a picture I have in mind how we can understand Lennon's-dual of the original cluster algebra. So, so we want to put everything we have set for the cluster variety thing into what Mark just mentioned, the toric model Bohr of toric variety. So we want to start with a toric variety. So we look at the fan. The fan for the A case are coming from this DIEI. For the X1 will be spanned by this minus DIVI. And then again here, we follow the exact same procedure. It's a bit long here, but it is just the exact procedure when we were talking about the rough story. We have a fan, we have a toric variety, And then the fan will give us, because this is a two-dimensional case, the waves here will give us the divisor, and then we bow it up. And here is the thing, the loci that we are bowing up are just the DI coming from the way of the fan. And here we are just looking at the zero locus of our mutation map. You can see those are just our mutation map. So this is the pawn, like here is just two-dimensional case. So those are all just pawns. We are just solving a one variable polynomials here. So so we'll look at the toric variety that are bowing up from this toric variety, the bow up of those toric variety from those pawns that we just mentioned. And then here, the final step, what we have is we take out the boundary of it, and this open piece are just isomorphic to the cluster variety that we usually understand, which is the Gouin-Tori procedure. So you can see that we can describe the toric variety either in terms of Gouin-Tori or as toric bow up of toric varieties. So this is our setup. So what with Sam, Hansol, and Yu-shen, what we do is we look at the rank 2 case. What we mean by rank 2 here is not dimension 2. The rank 2 here is the skew symmetric form is of rank 2. So that is we look at the kernel of the skew symmetric form, and then what we have is and then the kernel will give a torus action on the tori we have. And then what we want to do in this case, actually, instead of looking at the A variety, we want to look at the quotient of the A variety. So this is what we do. So yeah, this is what I said. We want to look at the quotient of this A variety under this TK action. So one thing we'll just do is we have the lattice, we just quotient everything by this kernel. And then we look at the fan as an image of this quotient map. So this is what we have. And then what we show is we follow the same procedure. We look at this fan, we bow up again. We are going to see we bow up again at the zero locus of the mutation map. And then this bow up of the toric variety will be isomorphic to the quotient of the A variety up to codimension 2. So this is a setup. So this is the fan that we are looking at after quotient. And then this is the thing we bow up at the divisor intercept again, the zeros of our mutation map. And here it is. Okay, here is fundamental theorem of algebra or root of unity. 1 plus x to the k. So we have k many root of unity. So we have k many or like index of vi many pawns, and the multiplicity will be coming from this index di ei bar. So the procedure we describe in Gross-Hacking-Keel fibres is we have this fan, and then the scattering diagram or the wall that we are looking at will be this span by this di ei bar, and then which di ei bar here. But here we might have multiplicity. So we are colliding all the walls. So we have this exponent here. I just want to mention one technical thing here. If this index is 1, that will be simple bow up. If it is not, that will be getting into the orbifold bow up case. But here, what we do as a cluster people is we just stare at this wall or this collection of wall, which is the initial scattering diagram. And this one here, look at this exponent here. We're talking like EI is something with the X mutation, and this DIEI is just a Lagrangian of the X mutation. So you can see is like this is just like the Lagrangian X scattering diagram, but not precisely, because you can see I have all the bar here, which is I'm just quotienting out something. So more precisely, what I'm having here is for this kernel K, actually, not only the K will give me the TK action on the A torus, it also gives me a fibration of the X torus. So actually what this scattering diagram is describing is the Lennon, this Lennon-Steel X family, which we are looking at the identity of this family. So this is what we have. Yeah, this scattering diagram will correspond to the Lennon-Steel XE scattering diagram, which is the fiber of the family of the identity in the torus. So what we have, you can see, roughly speaking, this is what we obtain, the quotient of the A cluster variety, a mirror to the Lennon-Steel X variety at the fiber E. Here I use the term roughly, as many of you will be upset because the algebra generated by theta function might not be finitely generated. So, okay, you are going to, okay. I know you are going to ask me this question then. But anyway, we do have the scattering diagram. In the case we have finitely generatedness, we do have an algebra, then we can take the spec of it. But even if not, we just have that anyway. Here is like, before that is all just algebraic geometry setup. But what we have with Sam Bardwell-Evans, Hansol Hong, and Yu-shen LIn, as I said, we show the equivalent between Lagrangian form mirror and the Gauss-Penner-Pendes-Sieber scattering diagram, that in the case of simple blowup of Taylor varieties. So in the case that when the blowup is simple, then this is a Lagrangian form mirror. So this is how we can turn everything from the algebraic geometry sense into family form mirror sense in using this set, and how we can see in the cluster picture. But this is the final slide I just added. It's kind of as a coherence of Mark's talk, because at the end of Mark's talk, he draws some picture like this, right? Like I just intentionally copy his picture from his talk. Like, let me use a chalk here. I think it's like answering Wes picture. We have something like that. Sorry, I don't know why does I know right chalk. Okay, here. And then Mark says something. We are gluing the Maslov index to this, and then when we glue together, we get something like this.
Would it be possible to see what Mandy is writing on the board, please?
Oh, I can write it, no worry. This is the picture we have. Yeah, maybe I should use it here, which is this thing, and then we glue it together. We got something like that. So about the Maslov index to this. So so because all I have been seeing before this line are just Maslov index 0 this. So the question is, can we say something about Maslov index to this? It turns out it's much more, the construction is much more difficult because we have some negative Chern class at the of the boundary divisor. But the case is if the boundary divisor doesn't have negative Chern number sphere, and then we have everything good enough, we do have the number of Maslov index to this agree with the kind of broken line in the Gross-Hacking-Keel construction. So you can see this is the picture of like writing the potential of this A2. I cannot fit the added way, but this is still the A2 example that we have. So this is what we usually talk about the theta function, right? Theta function is, you can see this pair, which is I look at the slope 0, 1. And this is what when Mark is saying, it just goes straight, the holomorphic this, right? And this one is when we go, it have this choice of bending over the wall, right? So this is our theta function, or like this, I'm drawing all those, you can see all those line, broken line I'm drawing here. Sorry, I just mean this one. You can see here it doesn't bend, and here it bend, which we can think of as this picture. I don't know, I hope it's clear. And then you can see all the initial direction I have are actually just coming from the wall of the scattering diagram. So this is how we can see the potential of this cluster variety setting. So what we literally establish the potential for all those cases. One thing is that as an introduction for the next speaker, there's like a separate project with Laura Bossinger, Tim McGee, and Veda Lajeta. What we show is we relate this construction, the GHKK potential, with the Koenig-Ridgely theoretic potential for Grassmannian by using the CARW duality introduced by Gong-Chen, which is the next speaker. So that's the end of my talk. Thank you very much for being patient.
Thank you very much. Are there any questions?
You are
okay. If there's a question in the room, it would be great if you could use the microphone so that we can hear.
Maybe I can. Are you asking how I can see the holomorphic disk Maslov index or the Maslov index? Okay, I'm not a. You can see I'm not a sympathetic people. It's about how those divisor intersecting the boundary divisor. So Maslov index is like 2 times the intersection. Oh. Okay. 2 times intersection. So for all our setup, we just work with the open piece. So it will be Maslov index 0. And then this last line, we take the boundary into account. Then we have the Maslov index 2. So I know it's a bit like, I hope that answers a bit your question. Okay, sorry. Maybe I should just use my computer.
Yeah, if you use your if you write on the computer, then I guess
that would be better.
Probably everybody could see.
Okay, I'm here.
Okay, so
I mean, in the A2 example, what is the boundary?
It will be the A2 example will be DP5, right? Then this will be the A2 example will be DP5. So we'll be trig of 5 minus 1 curve. So that is what you take out. Let me think.
What was the question?
The question is how or why DP5 is trig of 5 minus 1 curve. I don't know. There's a couple ways you can see it. You can either see it from like going back to the DP5 is P2 going up this and that, and then I don't know, and then when you blow up all those curves, and then you'll see that it's a DP5 or like. Oh, sorry. Yeah. I mean, like that's like more, because usually it's just you're very right. And then here is there's like one at toric. That's like 2 points on the toric blow up. So you got something like that, and then you blow up 2 more points, and then that is what you have roughly. A2, I mean, I guess it's the Custer A2 setup, this scattering diagram that you are talking about.
I think what you get is P2 case you have P1 cross P1, and one of the P1, each of the P1 you blow up 1 point. And you consider, as Mark said, probably you should consider the strict transform of the boundary of the P1 cross P1 in the blow up.
No, the question is why it is DP5, right? I guess to answer. Or
and then probably you need to toric blow up the intersection of the P1 again, and you get 5 boundary components. That's what I understand. Sorry.
I mean, what Mandy wrote down in this picture on the screen, the P2, you blow up 2 non-toric points and 2 toric points, gives you a blow up of P2 at 4 points, so it's DP5.
yeah, okay, this is like two toric point, 2 non-toric point. The two non-toric point will be the custom mutation you see, and then you have the 2 other points you see will be the blow up at toric point, and then you get the no, maybe mark here.
I think this. I don't think we can solve this in 2 minutes. I mean, we can talk about it.
I think I don't know that many way you can. But at least like bowling. Sorry.
Maybe we should discuss this
Yeah.
after.
Exactly. Maybe this is a discussion for the coffee break. We'll just take a 5-minute break until 2:36. And for the next talk, after which then we'll have a longer break where maybe this discussion can be taken up again. So thank you, Mandy, for your talk.